Hi, my name is Edenir Pereira Filho, and I am a professor at Federal University of São Carlos in Brazil. My contacts are here, my YouTube channel, LinkedIn, Instagram, my Facebook, and my research group. The goal of this presentation is to show some analytical chemistry developments using a J200 instrument from Applied Spectra. But what is a 200 equipment? This equipment leads with LIBS analysis, laser-induced breakdown spectroscopy. And since 2013, I am, together with my research group, developing some analytical chemistry methods for metals determination in several types of samples, like, for example, electronic waste, food, and also minerals. Okay, the motivation of this research is about the sample preparation. The best way to prepare a sample is not to prepare a sample. Then we can, using LIBS, perform direct solid analysis. But when solid analysis is performed, several problems be can occur. For example, interferences, spectral and matrix interferences, micro heterogeneity, how to select a calibration strategy, how to select appropriate standards for calibration, how to prepare the standards. Okay, how to minimize these limitations? We can use, for instance, several types of strategies. For example, chemometrics, that is a science dedicated to plan or select optimal experimental conditions to provide maximal chemical information with the data analysis. Using chemometrics, we can perform, for example, optimization, normalization or standardization of the spectra, multivariate models, univariate models, discover or rediscover calibration strategies, and also we can perform classification models. This is the goal of this presentation. In 2021, my research group and we published a free ebook. This ebook is entitled Laser-Induced Breakdown Spectroscopy LIBS, Applications and Calibration Strategies. I am one of the organizers, and this ebook was written in English, and also in Portuguese. And this ebook can be downloaded, free downloaded in this website. Or you can see in the description of this video, this link for this ebook. This ebook is divided in several parts. For example, sample preparation, optimization, data processing, univariate calibration, multivariate calibration, applications, considerations, conclusions, and perspectives. Then in this presentation from now, I will present these topics for you. Okay, the first topic, sample preparation for LIBS analysis. We can use, for example, liquid samples, solid, powders, for example, and how to prepare, what's the problems related to direct solid analysis. For example, we have minimal or no pretreatment of the samples. We can provide high analytical frequency for the analysis. We can reduce the risks of the analyte losses because we are manipulating less the sample. We can reduce the use of hazardous reagents and, of course, generation of wastes. We can use a small amount of sample, and we can have also spatial distribution of the analyte. And now LIBS can be in the team of several other analytical chemistry techniques, for example, graphite furnace, ETV, electrothermal vaporization, laser ablation with ICP-OES, or laser ablation with ICP-MS. Okay, how to prepare the samples, solid samples, for instance. We have several problems. For example, heterogeneous samples. In the majority of the problems, we need a grinding process in order to homogenize the sample. With homogeneous samples like glasses, alloys, polymers, we can present the sample directly to the instrument. And in the majority of the problems, we have a solid sample. We can perform a pellet. We can have a pellet. And with this pellet, we can also directly present this for the laser. In some cases, it is necessary to use a binder. For example, polyvinyl alcohol, for instance. We can have a binder in order to obtain a pellet, a more solid pellet for the samples. Okay, with liquid samples, we can form a film using a polymer, for example, PVA. We can mix the liquid sample with, for example, a carbon, wood, or we can have a freezing, electrodeposition, for example. We can perform a precipitation, adsorption of the solid sample, for example, in a substrate. We can present the sample with a liquid jet, for instance, freezing, and immobilization or encapsulation with PVA or paraffin. Okay, optimization. What we can optimize in the samples? For example, we can use design of experiments, DOE, in order to calculate effects and also regression models for the variables. We can calculate ANOVA table and also response surface methodology in order to find the best condition for an analysis. In my YouTube channel, here you can have the YouTube channel. You can see also in the video description this link. I have several tutorials and also free scripts for Octave and MATLAB and templates in Excel in order to perform the calculations of the models and also the effects of the variables. Data processing. What's the main goal of data processing? We can perform a variable selection, improve figures of merit. We can perform some mathematical transformation in the raw data, and also we can reduce signal fluctuations using, for example, normalizations. In my research group, we are developing several types of normalization during the last 10 years. These normalizations, the goal is to minimize the signal variations and sample matrix differences. I suggest, for instance, to collect more than 400, 300 of spectra per sample, and we are performing several normalization modes in order to minimize these problems related to micro heterogeneity. For example, the average is not a normalization, but when you have several spectra, for example, hundreds of spectra, we can minimize problems with heterogeneity. We can perform a normalization with the norm and then average. We can perform a normalization with the area and then average the data. For example, we can collect several spectra, calculate the mean of the data, or we can normalize by the norm and later calculate the mean, for example. This is the normalization tool in this list here. We can normalize by the maximum, by the line 193 or line 247. You can use in carbon here as an internal standard. And we can perform these normalizations here using the average or using the sum. Okay, the main goal is to, I like this joke here, is to transform the data, reducing the variation among samples with the same characteristics. Okay. In my research group, we also developed several routines for data normalization, for area and height calculation, and also to calculate the signal to background ratio. Okay, we have the 12 normalization, and with this 12 normalization, we can identify outliers. For example, we have here a sample, and here we have the signal 0, for example. We can identify the sample and remove the sample from the spectrum. And also we can calculate peak area and peak height of the samples and signal to background ratio. Okay, univariate calibration. We can have here several types of univariate calibrations, but I will describe some of them. The most common type of calibration is matrix matching calibration. Everybody should prepare a calibration curve, but in LIBS, we can prepare a calibration curve using, for example, solid standards. Then the idea here is to use in the x-axis the concentration, and in the y the intensity, and calculate a model, a linear model. We can use also internal standard, or we can perform also standard addition. These standards can be reference samples or certified reference samples, for instance. Or we can produce these standards mixing the samples with microcellulose to prepare the standards with different concentrations. One of the most used univariate calibration strategy in LIBS is MAC, multi-energy calibration. In MAC, we have a pellet with sample and a diluent. This diluent can be, for instance, silica, for example, and we have a sample and a standard mixed. We have two pellets. In the x-axis, we have the sample plus standard. We can mix this in a 50-50%. And in the y-axis, we have the sample and diluent. And we collect several emission lines signals from the analyte. For example, if we are trying to determine chromium, we can calculate it. We can collect several emission lines for chromium and produce a linear model. The slope of this linear model is used to calculate the concentration of the analyte in the sample by using this equation here. Using MAC, we can identify spectral interference. This strategy was used for the first time in ICP OES for liquid samples. And using LIBS, we analyze mineral supplements, electronic waste, and also ores. The other strategy is two-point calibration transfer. In two-point calibration transfer, we prepare pellets of the sample and also of the standard. The standard can be reference samples. And we perform several numbers of pulls. For example, 100 pulls here, 200 pulls here, and we can calculate a linear model for sample and for standard. And the analyte concentration will be the slope of the sample divided by the slope of the standard times concentration of the analyte in the standard. We use this strategy in order to calibrate hard drive magnets. We are interested in determination of hard earth elements. Fluence calibration. Fluence calibration, we use two different Fluence 1 and Fluence 2, in order to normalize the plasma. We have in the x-axis the signal, the fluence for standard, the signal obtained in Fluence 1, the signal obtained in Fluence 2, and in the y-axis we have the signal of the analyte for the sample in Fluence 1 and in Fluence 2. We can have also a plasma normalization, and using this equation here, we can calculate the analyte concentration, the slope of this linear model times the concentration of the standard of the analyte in the standard. We know this, and then we can calculate the concentration in the sample. We use this strategy in fertilizers and also in electronic waste. Multivariate calibration. Multivariate calibration, we can improve the precision and the robustness of the methods. It's possible to handling with interference if the interference are in the calibration model. We can use several emission lines from the same analyte. As using LIBS, we can record several emission lines. For example, in the 200 instrument, we can record emission lines from 186 to 1042 nanometers, since the ultraviolet up to the infrared, passing here for the visible. Okay, and we can also use several emission lines. For example, chromium, iron. These analytes have more than 100 visible emission lines in this range using the J200 instrument. The most used multivariate calibration is PLS, partial least squares. Is the most used. We can use several emission lines. It is necessary reference samples in order to prepare a calibration data set. Interference can be handled if present in the calibration data set, and we use this in several applications, like polymer analysis, for example, and also for metals determination in sunscreen, for example, in paints, in several types of samples. In the last year, we developed, or better, we used geometric strategy named unfolded partial least square with residual bilinearization. The main goal of this calibration strategy is to perform a residual bilinearization at the end of the model in order to remove unwanted components. We can improve the figures of merit of the analytical method. And we can also use a mixture of salts in order to have a calibration data set. In PLS, for example, it's necessary, for example, a calibration data set with the same matrix of the samples. In UPLS, RBL, we can prepare a calibration dataset with a mixture of salts and use the RBL at the end in order to remove unwanted components. Parallel factor analysis, PARAFAC. In PARAFAC, also mathematically remove interference. It's necessary a data array. We can prepare this data array using emission lines in one mode, emission lines, different delay times, for example, and we have a signal. Or we can have different positions. We can have different positions of the sample, and you have here the array for this type of data. And we can identify interference and remove this interference in the sample. Data fusion. Data fusion is a very good strategy. We can combine, for example, different techniques with different natures. For instance, we can combine LIBS. LIBS is an emission technique with X-ray fluorescence that use X-ray fluorescence, and also laser ablation ICP MS, where you have the mass ratio as data. We can make a fusion of this data in order to obtain a model, a calibration model with better figures of merit. We perform this for electronic waste analysis, combining LIBS, X-ray, and also laser ablation. Okay, now some applications for this data, for this type of technique. We have several applications for food analysis, and the analytes are, for example, calcium, potassium, magnesium, and phosphorus. We also performed an analysis of seeds, cocoa, and also flour. In the literature, you can see, for example, beef authenticity using LIBS, for instance. Electronic waste calibration. We have some applications for antimony and lead determination in polymers, aluminum, copper, iron, and lead in PCBs, printed circuit boards, indium determination in LCD screens, and also boron, iron, and rare earth elements determination in hard drives of the computers. Sugarcane evaluation. We use LIBS in order to determine the fiber, the quantity of fiber in sugarcane. And also fertilizers. We use LIBS in order to identify contaminants, macro and micronutrients in fertilizants. And also we also analyze liquid fertilizants encapsulated using PVA. The main goal was to verify contaminants, micronutrients, and micronutrients. Okay, now a very different application, the use of LIBS in archaeological applications. Here we have a coprolite. Coprolite is feces of dinosaurs, for instance. And then we have here the rock in the coprolite here in the middle. We can perform several laser pulses in several points, and we can perform principal component analysis in order to verify the composition, qualitatively, the composition of the sample, what we have here, what is different from here. You can see, for example, what this animal ate several years ago, for instance. And now considerations, conclusions, and perspectives. Conclusions and perspectives. Using LIBS, we have new frontiers, for example, space exploration, underwater exploration, data mining. We can solve complex problems using LIBS and also combine with kinematics. We can use the imagination and cooperation among areas, chemistry, physics, and mathematics in order to solve complex problems. I can imagine, for example, several opportunities, ideas, and challenges using LIBS in several applications. And here we have my research team, the team that work with the J200. Here we have the J200, this instrument. I can open this little door here and introduce the sample inside the instrument. We can use, for example, a sample like a cell phone, for instance. And here the people that work with me in these last 10 years performing these applications. Thank you very much for your kind attention. Thank you very much also to FAPESP and also other financial organizations like CAPS and CNPq. Okay, thank you very much. And if you have some questions, please send me an email or we can discuss this in person during the meetings. Thank you very much.